In this video, we will explore relationships between points and planes. The relationships between points and planes are somewhat similar to what we can find for the relationships between points and lines. We can find the foot of perpendicular of a point to a plane, the shortest distance between a point and a plane, and the point of reflection about a plane. One extra item here is that we can find the shortest distance from the origin to the plane. Although this can be found using the method outlined earlier for finding the shortest distance from the point to the plane, we can employ a much faster formula to achieve this, as we shall see later. If we have a point A with coordinates 1, 0, 3 and a plane r dot 2, 0, negative 1 equals to 4, and we want to find the foot of perpendicular point F, the steps are different from that of foot of perpendicular from a point to a line. Firstly, we form the equation of a line that passes through points A and F, which means it is parallel to the normal vector of the plane. So we have the line over here, which is parallel to the normal vector, and we can say that line AF has an equation of r equals to 1, 0, 3 plus lambda 2, 0, negative 1, and lambda of course is a real number. Next, we notice that the foot of perpendicular is actually the intersection point of the line AF with the plane. Thus, we can solve for the intersection point, and this will give us the position vector of the foot of perpendicular. So we can say that OF will have coordinates of 1 plus 2 lambda, 0, 3 minus lambda, and since OF lies on the plane, 1 plus 2 lambda, 0, 3 minus lambda, dot with 2, 0, negative 1 must be equals to 4. And thereafter, we can do an expansion, 2 plus 4 lambda minus 3 plus lambda equals to 4. And solving this equation gives us lambda equals to 1. And if we substitute this lambda equals to 1 back into our equation for OF, that will give us the position vector of F, which is the foot of perpendicular. So therefore, OF will be equals to 3, 0, 2. In example 1a, we are going to find the foot of perpendicular from point A to the plane pi. So let's draw a simple diagram. I have this plane over here, pi, which has equation of r dot 1 minus 2, 4 equals to 3, and the point A over here, 1, negative 4, 9. Notice that I don't draw a full 3D diagram for this because whenever possible, I try to draw the diagram in a simpler manner so that it's easy for me to interpret. So with this, what I want to find is the point F, and recall that in order for us to find point F, we need to first form the equation of the line AF, which will be r equals to 1, negative 4, 9 plus lambda 1, negative 2, 4, and lambda is a real number. And based on this, I can say that OF will be equals to 1 plus lambda minus 4 minus 2 lambda 9 plus 4 lambda. And since point F lies on the plane, 1 plus lambda minus 4 minus 2 lambda and 9 plus 4 lambda dot with 1, negative 2, 4 must be equals to 3. And if I expand this dot product, I will get 1 plus lambda plus 8 plus 4 lambda plus 36 plus 16 lambda equals to 3. And this gives me lambda equals to negative 2. And if I substitute this lambda equals to minus 2 into my equation for OF, I will get OF equals to minus 1, 0, 1. The shortest distance from a point to a plane can be found by finding the length of the vector AF, if we know what is point OF. From earlier, we know that OF is equals to 302, and based on this, we can find out what is vector AF. AF will be equals to 302 minus 103, which gives us 2, 0, negative 1. And finally, once we get vector AF, the length of vector AF will be the shortest distance that we are looking for. So therefore, shortest distance will be equals to mod AF, which will be equals to mod of 2, 0, negative 1, which is square root 5 units. Example 1b is a continuation of example 1a. In example 1a, we have determined that the foot of perpendicular from point A to the plane is negative 1, 0, 1. Therefore, we can find out what is vector AF. AF will be negative 1, 0, 1 minus 1, negative 4, 9, which becomes minus 2, 4, minus 8. And therefore, the shortest distance will be equals to mod AF, which is equals to mod of negative 2, 4, negative 8, which becomes square root of 84 units. As with the case of the shortest distance between a point and a line, we have a shortcut method to find the shortest distance between the point and the plane if we are not required to find out the foot of perpendicular. To use this method, we first find a random point B on the plane. There are many combinations that we can use, but I like to keep things simple, and therefore I will usually make two of the components 0. And in this case, I would let OB equals to 2, 0, 0. Next, I can form the vector AB, and AB will be equals to OB minus OA, which gives me 1, 0, negative 3. Finally, we note that the shortest distance is the length of projection of vector AB onto the normal vector of the plane. Thus, we can apply the formula of mod of AB dot n cap to find the shortest distance. So we can say that the shortest distance equals to mod of AB dot n cap, which is equals to mod of 1, 0, minus 3 dot with 2, 0, minus 1 divided by mod of 2, 0, minus 1. And if we expand and simplify this entire thing, we will end up with square root 5 units, which is exactly the same value as what we have found in the earlier example. Note that the difference between this and the formula for finding the shortest distance from a point to a line is different. It is a dot product over here since we are looking at the length of projection, whereas it is a cross product when we find the shortest distance between a point and a line, since it is finding the length of rejection. In example 2, we are going to find the same shortest distance between the same point A and the same plane pi, but using the second method that we have just learned. So now I have the plane pi such that r dot 1 minus 2, 4 equals to 3, and the point A will be 1, negative 4, 9. The first thing to do is to find a point on the plane, and I'm going to let this point be 3, 0, 0. So once I have this, I can form vector AB. Vector AB will be equals to 2, 4, negative 9, and therefore the shortest distance will be equals to mod of 2, 4, negative 9 dot 1, negative 2, 4 divided by mod of 1, negative 2, 4. Now if we expand and simplify, this becomes 42 over square root 21, and of course 42 over square root 21 is the same as square root of 84. And this is the same shortest distance that we can find from example 1b, and thus proves that the two are exactly the same. The outline for finding the point of reflection about a plane is the same as that of finding the point of reflection about a line. We must first find the foot of perpendicular from the point to the plane. However, do recall that the steps for finding the foot of perpendicular are different from that as with finding a point and a line. From earlier, we know that OF is equals to 302. Once we find OF, the next would be to again identify that point F is the midpoint between point A and A prime, and therefore we can use ratio theorem to come up with this equation over here. And once we have this equation, we can rewrite this equation to find out what is OA prime. So we can say that OA prime is equals to 302 minus 103, and this gives me 501, which is the position vector of the reflected point. In example 3, we are asked to find the point of reflection of point A, 1, -4, 9, about the plane pi. So first we have to find out the foot of perpendicular, which we have found earlier, -1, 0, 1. And based on A and F, we can therefore find out what is A prime. So we know that OF equals to OA plus OA prime over 2. This gives us OA prime equals to 2OF minus OA, which is the same as 2, -1, 0, 1 minus 1, 4, 9. And therefore, OA prime will be -3, -4, -7. When finding the shortest distance between the origin and a plane, we can use a simple formula instead of repeating the steps that we have done in example 2. For any plane with the equation of r dot n equals to k, we simply have to divide the entire equation by mod n, such that we get r dot n cap equals to k over mod n. And this term on the right hand side will be the distance between the origin and the plane. One thing to note is the sign of this term. If you have two planes with different k values but the same sign, this means that they lie on the same side of the origin. So I might have this case of an O here, r dot n cap equals to 4 here. I might have another plane that is further away from this first plane, r dot n cap must be equals to a value that is larger than 4, so probably 7. And if I have another plane that lies on the opposite side of the origin, maybe somewhere over here, then I know for sure that this term over here must be a negative term because they are on opposite sides of the origin and they must have different signs. Now, based on this formula, this shortest distance over here will be simply 4 over mod of 2, 0, -1, which is 4 over square root 5. In example 4, we now have to find out the shortest distance between the origin and the plane pi. R dot 1 minus 2, 4 equals to 3. So we are interested in this distance over here, which we can find very easily. It will be equals to 3 over mod of 1, -2, 4, which becomes 3 over square root 21 units.